Okay, so let's, okay.
This is a hypothetical impossible
Let's,
situation.
okay, back 2.1, 2.1, the concept of the limit. Okay, so this, as I said last time, is the most important idea in calculus. Okay, the idea of calculus, right? This is the idea that separates calculus from all previous knowledge. Although that's not exactly right, because Archimedes actually used something very close. Archimedes, it seems, was sort of on the border of discovering the notion of limit, thousands of years before. It's kind of interesting that the way they found this, as I understand it, was that in the late 19th century, they found this manuscript, and it was palimpsest, which was some sort of medieval erasable manuscript. So you could write something, and then you could write something on top of it, and then write something on top of it. And so what they found was that underneath, the top layer was actually an old copy of something of Archimedes that detailed something that's called the method of exhaustion. And I haven't looked at this myself, so I can't really tell you exactly what it is. But I can't tell you, really what it is. But what they say is that this is basically very close to the notion of limit. So amazingly, okay. So the limit that we're going to talk about, the notion of limit that we're going to talk about, is actually due to a man named Weierstrass. Okay, so Karl Weierstrass in the 19th century, this sort of fixed some of the problems that were introduced when Newton. So the way Newton talked about limit was in terms of infinitesimals, right? In terms of things that were infinitely small. And this bothered a lot of people, because what does it mean to talk about the ratio of things that are infinitely small? But Weierstrass in the 19th century introduced the notion that we're gonna give you, and this fixed everything, basically. Okay. So okay. So this section, I should say, is sort of like a touchy-feely section. It's not. It will give you the rough idea of what the limit is, but it's not going to give you exactly what the limit is. Okay. So it consists. You notice that Krantz says the concept of the limit. He calls this section the concept of the limit. He doesn't say the limit, and there's a reason for that. It's just at this point, it's just the concept. Okay. So some of you have probably seen this notion before. Somebody just asked you, what does the limit of f of x being L as x approaches C mean? What does it mean? Or maybe you've read it already. What does it mean that you have some function, and as the input approaches, the limit as x approaches C of f of x is L. What does that mean to you? Does anyone to dare a guess? How many of you have seen this before?
What is C? Is it like H?
Okay.
I know, but what is exactly C in this situation?
C is a value, so a fixed value. So here, x is your variable, C is a point. Okay, Richka.
So it basically means as x approaches, whatever that C value is, that means the limit will approach that L, which is on the y.
Okay, so as x approaches C, f of x approaches L, right? As x approaches C, f of x approaches L, right? As the inputs approach this place, the outputs approach that value. Okay. right? And so you have this picture, right? You have some picture. Usually they put a hole there. It's not necessary to put a hole there, but let's put a hole there. So as you take different x values, here getting closer and closer to C, here's L say, the outputs, you see the outputs get closer and closer to L. Right? Okay, so yeah, so that's maybe the rough way of talking about what the limit is. So let me make one remark. Why did I put a hole here? Those of you who've seen the limit before. Maud?
That's where the function is undefined.
The function could be undefined there. The thing is that the limit is not, to say the limit is L doesn't say anything about the function's value at C. Okay, so this does not imply anything about the value of f at C. Okay. So yeah, so it does not imply anything about the value at C. So that's my remark. My symbol here, remark. Doesn't imply anything about the value at C. At the University of Chicago, I heard, although I don't think I saw it, that there was like bathroom graffiti that says something like this: the limit of fun of x as x approaches the University of Chicago is 0. But I should say that this is very ignorant graffiti, right? Because it doesn't say anything about the fun at the University of Chicago, which may well be incorrect, right? Maybe some large value. Right? It may be that the fun at the University of Chicago could be 1 billion. Okay? 100,000. Right? So, right, because to say that the limit is 0 simply means that as you approach the University of Chicago, your fun tends to 0, which is probably true, which may be true. Yeah. When I first got to the University of Chicago, in the orientation for graduate students, they said, do not cross 47th Street in the north or 61st Street in the south, otherwise you will be killed. Yeah, and a student from China came to me afterwards, and he said, I've never heard such a statement in my life. 因为肯定死 you'll definitely die. It sounds really humorous in Chinese. Okay. So in any case, so it doesn't imply anything about the value at C itself, so let's just go through some examples. I think the examples that the authors give you are very good. Each sort of illustrates a different point about the notion of limit. So the first example that they give is the following. F of t is t squared. G of t is t squared for t not equal to 0. Okay. H of t is t squared for t not equal to 0, and is 1 when t equals 0. Okay. And they want you to consider the limits of f, g, and h as t goes to 0. Okay, so they've got these 3 functions, right? So your picture is like f is the parabola, f is your sort of standard parabola, g is your parabola, but it's not defined, right? So g is the parabola, but it's undefined at 0, at t equals 0, and then h is defined at 0, but takes the value 1 there. F, G, and H. Okay. So, what do you think are the limits as t tends to 0? What are the limits as t tends to 0, Robert? Yes.
0.
0? Okay. So say that 0. Right. And why do you say that?
Because you just get closer and closer to 0.
So you're looking at the graphs, right? You're saying, well, look at the graphs as you take values closer to 0. You think, but I've just erased the graphs. Okay, I've just erased the graphs. So why? And I'm blind. Okay. So how do you convince me that that these things actually do tend to 0? Here's one way. You say, well, look. So we say, here's what we think, right? The limit of each is 0 as t goes to 0. Okay. And so here's how you might argue. Here's how you might argue that. Okay. You say, well, let's look at consider, say, the absolute value of t squared. The absolute value of t squared. Right. Let's consider the absolute value of t squared as t goes to 0. Well, the absolute value of t squared, that's the same thing as absolute value of t quantity squared. Right? The same thing as the absolute value of t quantity squared. Right? And I'm going to say that that is smaller than the absolute value of t. Is that true? Is that true? The absolute value of t squared is smaller than the absolute value of t. Ellen?
If it's less than 1.
If the absolute value of t is less than 1, yeah, that's true. Right? But it's not true. It's not true in the general case, right? But certainly, we can say, we're heading towards 0. So as we head towards 0, at some point, all of our t's are going to have absolute value less than 1, right? So this is true, right? So this is okay as long as we are close to 0, which we know will happen because our t is heading to 0. Okay. And then you say, well, look, as t goes to 0, the absolute value of t goes to 0. Right? This thing goes to 0. And so that forces the absolute value of t squared. What does that do to the absolute value of t squared? That shows that the absolute value of t squared goes to 0, right? Because the absolute value of t squared is some non-negative number, and it's smaller than the absolute value of t. And so, it's smaller than the absolute value of t, which it's bigger than 0, bigger than or equal to 0, and smaller than the absolute value of t, and the absolute value of t goes to 0, right? So the absolute value of t squared also goes to 0, right? So the absolute value of t squared also goes to 0 as t goes to 0, right? And that forces t squared to go to 0 also. So t squared goes to 0 also. Okay. So this is this is one type of argument. Right? How would you convince somebody algebraically that this happens? Well, you'd say, well, I'm trying to show that this thing is, the values of this are going to go to 0. I know that the size of these values is smaller than this, and this thing goes to 0. So the size of them becomes arbitrarily small also. So they go to 0. Okay. Are there any steps that people don't follow? Any questions? Okay. Oh yeah, Edie.
Would this be considered to be an algebraic proof?
Yeah, well, this is, I mean, at this point, no, I'd say. At this point, no. It's sort of like, you know, an argument, but at this point, it's just a sort of like, this thing gets smaller, you know, it's not, it doesn't qualify as a proof, I'd say. Yeah. It's rather sort of like trying to convince you. Yeah, Evelyn.
I'm not understanding
Yeah.
why your t squared is going to be less than your t.
Yeah. Okay, so look at t squared. Obviously, value of t squared is this, right? Right? And if the absolute value of t is less than 1, then one of them, I'm going to say, is less than 1, right? So the product is going to be less than t, right? If you take something and multiply it by something smaller than 1, then it becomes smaller, right? If I take the absolute value of t and multiply it by 0.5, I get something that's smaller than the absolute value of t, right? So I have the absolute value of t, and I'm multiplying it by itself. Itself happens to be smaller than 1. So I get that the product is smaller than the absolute value of t.
Oh, so that's why you said it's only true if it's less
That's right. It's completely false otherwise, right? If t were equal to 3, say, right, is 3 times 3 smaller than 3? No, right? But if I'm looking at a half, certainly a half times a half is smaller than a half, right? Because I'm taking the half and multiplying it by itself, which is something smaller than 1. Okay, yeah, Leanna.
So I'm confused about like second step. Sorry.
Yeah, sure.
So are all of your t's after this point that you just explained in terms of less than 1? Or
Yes.
Okay.
Yes. Yes.
Okay.
Yes. Yeah, because that's sort of included in the as t goes to 0. Right, as t goes to 0. As t goes to 0, your t's are going to eventually become less than 1 in absolute value. Yes, Sam?
So it's vital that the square be outside of the absolute value in that first step.
Yeah, because you want to think of, I mean, it's certainly true. It's certainly true that if you take the absolute value of the square, it's the same thing as the square of the absolute values. And you need that to make this observation.
Oh.
Yeah. Okay, so that's one example, and then so that tells you about f, and it certainly tells you about these other guys too, because you don't really care. You know, the point of including these other guys is that you don't care what happens at 0 itself, right? So all of these guys go to 0 by the same argument. Okay. The second example that's given is this one. The limit of x squared minus 6x plus 6 over x as x goes to 5. Okay. And what the authors say is that, well, okay, we take some numerical approximations. They say let's plug in some values close to 5. Right? Let's plug in some values close to 5. And you see that basically what happens is that this x squared is basically like 5 squared, right? X is basically 5, right? So x is basically 5. So x squared minus 6x plus 6 over x is basically 25 minus 30 plus 6 over 5, right? That's 1/5. Okay, and they show that this actually works by plugging in some values close to 5 and saying that they actually do tend towards 1/5. So they verify this. They verify this numerically. Well, they don't really verify it, but they sort of give evidence for this. Yeah, they give evidence for this limit being 1/5 numerically. Right? So, so what this seems to say is that, what is this saying? So, implication? It seems to say that the limit, let me say it this way, functions will tend towards their value, towards their values at C. Right? That's what it seems to say. It seems to say that you can just plug it in. Right? You just put in the 5 here. Right? Okay. It seems to say you can just plug in 5 here, and then that will be the limit. Right? It seems to say that if you want the limit of the function, you just evaluate the function at that point.
Didn't we say that it doesn't actually say anything?
Yes,
about
thank
that
you. Okay, yeah, but we just said that the limit may not have anything to do with the value of the function at that point, right? Okay, so you have to be a little bit cautious, right? And say some functions, right? Some functions will tend towards their values at C, right? So for some functions, you can evaluate them by just plugging in. And then that sort of opens the question, which, right? That turns into a question. Which functions can you determine the limits of by just evaluating them there? Okay. Second, it seems to imply that the limit of a quotient is the quotient of the limits. Right? That if we want this limit of the quotients, we just evaluate the top limit and divide it by the bottom limit. Right? Is that true? Third, it seems to say that numerical approximations can give some idea of the actual limit. Okay, so those are all things that seem to be hinted here. Are they true? We'll find out. We will see.
What does the third one say?
Sorry. Numerical approximations can give some idea of the actual limit. Okay. Example 4 goes like this. The limit of x squared minus 4 over x plus 2 as x approaches minus 2. Okay. So look at this one, and you say, well, what can we say about it? What would you like to do, Cynthia?
Blah, 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 so that's what I do.
Okay, so certainly this thing doesn't make any sense at x equals -2, right? Because the bottom is going to be 0, right? Okay, Amaya?
You can factor the top and cross them out and then plug in -2.
Okay, okay. Michelle?
Oh, I was going to say this.
Okay, very good. Okay, so so this is one of the things. So this is sort of a trick, right? You might, from the previous thing, say, oh, let's just plug in the values, right? Let's plug in -2, but you see that in fact, that won't work. Right? This is not one of the things that. This is not one of the functions that you can evaluate at the point to figure out what the limit is. Okay. Okay. But you can make the following observation, which is that we can rewrite this like this. We can factor the top, right? Into x plus 2, x minus 2, a difference of squares, right? And then you say, well, look, as long as x is not negative 2, then it makes sense to cancel these things, right? These things are non-zero numbers, right? As long as x is not negative 2, and we're actually, x is never negative 2 when we're talking about the limit, right? The limit is only talking about as x approaches negative 2, not x at negative 2 exactly. Okay? So it's okay, it's perfectly legal to cross these things out. Okay? Because x is never equal to negative 2. Okay. So this turns into the limit of x approaches negative 2 like this. And this turns out to be one of those things where you can just plug it in and evaluate, so you get negative 4. Okay. Yes?
When you cross out the x plus 2 on the top and bottom, would that imply a hole in the graph at negative 2?
Yeah. So the graph of this, what is this function? Right, this function is this function, right? This function is this function, which is undefined at negative 2, right? It's undefined at negative 2. It's undefined at negative 2. And let's see, so it crosses x minus 2, so just like this, right? It's just a line with a hole in it, right? It's just a line with a hole in it, right? So, sort of what we're saying here when we cancel these things out is that the limit of this guy is the same as the limit of this guy as you approach negative 2. Right. That's exactly what we're saying. That we can we don't really care what happens at negative 2 itself. Right. So okay. So this is just to re-emphasize the point that the limit doesn't depend on the value at that point exactly. Okay. Okay. The last examples are the most important. Okay, so think about your picture. You have some picture, right, like this. Right. Here is C. This height is L. Say the limit f of x is L as x equals C. So maybe there's a hole there. I'm gonna fill in the hole just for now. Okay. So so here's the idea. If the limit is L, one should be able to answer the question, how close to C must x be to ensure f of x is within 0.1 of L. Right. If the limit really is L, you should be able to answer this question, right? If you're saying that as you get closer and closer to C, then your values get closer and closer to L. If somebody says, well, how close do you have to be to C to get to have values within 0.1 of L? You should be able to answer that, right? If this limit, really is L, right? If somebody says, I'd like your values. You're telling me that the limit is L. Well, I'd like all your values. I'd like you to tell me how close do I have to be to C to ensure that all your values stay between these two lines, right? Stay where the height of the line is 0.1. Okay. And looking at you and just looking at your graph, say, oh well, look, as I can do that, right? I can find some distance to C, so that if I'm that close to C, if I'm any point that's close to C, all my values lie within 0.1 of L. Okay. Does that make sense? Rachel, what's your question or what's your comment? No? Okay. Okay. So, right, if the limit really is L, then you should be able to answer this sort of question, right? Right. And in fact, you should be able to answer it for 0.1, right? If somebody says, well, how close do I have to be? How close do my inputs have to be to C to ensure that my outputs are within 0.1 of L, right? And you should be able to answer it for 0.001. For any number, right? For any tolerance here, you should be able to say, if the limit really is L, you should be able to give an answer to, you have to be this close to ensure that that tolerance is satisfied. Okay. And this turns out to be the best way of thinking about the limit. Okay. This is basically Weierstrass's idea of what the limit is. Okay. So this is the crucial observation about the limit that one takes as the definition of the limit. That one takes as its definition. Okay. So let me do a simple example that hopefully will make this transparent. Right, you have some function 2x, right? 2x, and let's say that x goes to 3. Right, the limit of 2x is x goes to 3. Well, what's the limit of 2x as x goes to 3? 6, right? You know it. Okay, so you know it, but or at least you have some idea of what it ought to be. Let's see if we can actually answer this question, right? So we have your function here, 1, 2, 3, 6. Right, you have the 2x function, right? Right, this is 3, this is 6, and somebody says, what condition x minus 3 is smaller than d would ensure that the outputs are close to 6, within 0.1 of 6. What condition, what distance, this is basically saying, what distance to 3, right? What distance to 3, right? What distance to 3 would ensure that f of x, the output distance to 6 is less than 0.1. So I'm just taking I'm taking this language and I'm writing it using the distance, the language of distance, the notation of distance, the absolute value. Okay. Does everyone, so just to make sure, everyone see that this is the same, basically the same thing? Right? This is saying the distance to 3 is less than d. So we're asking what d, right? So what distance d? Right. So we're looking for the interval 3 plus d, 3 minus d. Right. If you blow this up. Right. What distance d would ensure that the outputs, right? What distance d would ensure that if you're within that distance of 3, then your outputs are within 0.1 of 6. Samantha.
So D in this example is the tolerance in the other example?
That's right. D is the tolerance. Yeah. Yeah, and it's usually written with a delta, a little delta. So usually written as the Greek D. So D is the tolerance. Oh, no, I'm sorry. This is the tolerance. 0.1 is the tolerance, right? Because you want your outputs to satisfy the tolerance. Sorry. Yeah. D is the how close to C, right? How close to C must X be? Alfred, are you going to ask a question or are you going to answer it?
I have a question.
Okay, yes.
So could you tell me if negative 6.1 equals 2x and 5.9 equals 2x and just solve for it?
Mm-hmm. Sure you can. Sure you can.
Okay.
So, so let me say it like this. So suppose I say, suppose I make suppose I make my tolerance 2. Okay. Suppose I make my tolerance 2, and I say I'd like all your outputs to stay within 4 and 8. Right? I'd like all your outputs to stay within 4 and 8. How close do I have to be to 3 to ensure that? How close do I have to? Don't put out the answer. Think for 1 minute, and then tell me. To ensure that the outputs lie between 4 and 8, that is, the outputs lie within a tolerance of 2, how close do the inputs have to be to 3? Think for half a minute, and then give me an answer. Okay, somebody like to give an answer? Leanne?
X has to be 4 and 2.
X has to be between 2 and 4, right? So the distance to 3 is 1, right? So to ensure that 2x minus 6 is smaller than 2, we need x minus 3 to be smaller than 1. Right? Okay. Is that clear to everybody? Right? As long as I lie between 2 and 4, as long as my distance to 3 is smaller than 1, then my outputs are within 2 of 6. My outputs distance to 6 is smaller than 2. Okay. Okay. Suppose I said, what about I'd like the outputs to stay within 0.2 of 6. So between 5.8 and 6.2. Well, how close do I have to be to 3? Ellie.
It's 0.1.
Yeah, it's 0.1, right? We need x minus 3 smaller than 0.1, right? Does everyone see that? Right? And suppose I say smaller than 0.1. How close do we have to be? Have to be 0.05, right? Have to be 0.05. Right? And suppose I say my tolerance is epsilon, some number. Well, how close do you have to be? Half of epsilon. Okay? Epsilon over 2 will do. Okay? And what you see is that if somebody gives you a tolerance, then there is a distance to 3 that works for you, right? Given any tolerance, there is a distance, so that if the distance to 3 is smaller than that that distance, then the distance of f of x to the limit is smaller than the tolerance is satisfied. Okay? Right? And you see it in this one example, and this turns out to be actually the definition. This actually turns out to be the definition of limit. Okay. So I'm going to this is by C. Okay. Okay. We'll talk more about this. Next.